Bismillahirrahmanirrahim. Now we will see the first finding of motor direct online starter. First finding exercise. So this is the first finding exercise of motor direct online starter. This is the power circuit and this is the control circuit. Okay. Now this would be the HMI. I have made it already. So I will show you. Now this is the program in ladder. Start button, stop button, thermal overload contact and motor coil, output coil, and it's normally open contact here. Tags are, these are the tags. Since these are all digital inputs and outputs, we have M bit. M bit here it is used because of memory bit. I have not used here input because I am not downloading it in the PLC. I am just simulating in the program. This is the output motor and this is again input, and thermal overload is another input contact. So this completes my program. Now I run it from here. Now it's asking for the CPU. So first of all I have to start a CPU here. So for that now this is the CPU and I am making it on. Again I try to download it. It's getting a file first and then it will be downloaded. Now we have to make it run. Now we will test it. Yes, it's working. Okay. Now the HMI part. Since I have already made it, I have used 3 objects here, 2 buttons and 1 animation. For button, we will go to the events. Events. Press, set bit, release, reset bit, start bit. Similarly, for stop bit, we will be having stop for press, set bit, and release for reset bit, stop. For motor, we will have the animation, 2 animations, clearance, 0 for red and 1 for green. Okay, that's fine guys. Now that's a simple HMI design. Now we will start simulation. If there is actual HMI, we will compile it and then download it in the HMI. 0 error and 8 points, so we must not have an error there. So it has started now. It's working. This is HMI working in simulation form. We can observe it here. Start. Stop. Start. Stop. So this is the first exercise of our simple direct online motor starter circuit. Thank you very much for listening. Hello guys, now we will discuss the other example of star delta starter. So the star delta starter, how does a star delta starter works? The motor, this is a basically reduced voltage starter to reduce the amount of inrush current, that is the starting current that the motor takes. So in the start configuration, the contactors, main contactor and the star contactor are on, and delta contactor remains off. So the motor gets started on Y configuration. In Y configuration we have reduced voltage to the motor windings. Now after some time, normally 7 seconds, so after 7 seconds the starters, the contactors, the star and delta contactor, they switch their positions. The star contactor gets off and the delta contactor gets on. So this is the ladder of this control circuit. In the PLC we have the main rung, which is start stop button and thermal overload contact and main rung, and the main rung contact in parallel with the start to get it latched. Then we have a timer and a timer pulse. We have a pulse timer here, and its input is main rung, and when the main rung is on, you push the start button, it gets on, and it starts the timer pulse. So timer pulse, we have set the time to 7 seconds. So for the 7-second queue remains, becomes activated. After the 7 seconds, we have used in the network 3, it's not be closed. So when the queue becomes 0 after the timer pulse, the start, you see the delta contactor, it gets on. So this is how star delta starter contactor works. Star delta starter control system works in the PLC. Now I have implemented this and show you its simulation. We are simulating in the simulator, not in the actual PLC. So what I will do is, first of all I'll show you the tags. These are the tags: start tag, star motor start contactor tag, stop, delta, and this is the thermal overload. All are boolean types of 0 and 1. So here I have used the memory bits instead of the inputs. Now it's program block. I'll show you the program block. This is the program block here, and it's HMI. You can see the HMI here. Events, we have to configure the events for the buttons, for the animation, for the display devices. We will be needing the animations. Okay, so I download it to the PLC. run the CPU and also go to online. Now it's working here. So at the HMI I will start simulation. It will get first compiled. Now here, this is the HMI. I will show you the working parallel. Now this is the start button. Here I have pushed it. This is a push button. Now this is start contactor. After 7 seconds it is switched. I will demonstrate you again. So this is how the start delta started. Hello guys, now we will discuss the third example of the PLC exercise program, that is a single traffic light control. Here we have two push buttons, start or stop to on or off our PLC traffic lights. Here we will be having three colored lights, green, yellow and red. The green light will be lit for 10 seconds, and then yellow light for 3 seconds, and then red light for 5 seconds. So this is the program here which have been implemented in the PLC. Here when we press the start button, it sets the green light bit on, which is M0.2, and in the meanwhile also gets start to the timer. The timer now runs for the 10 seconds, which is the on delay timer. When the 10 seconds have been passed, it resets the green bit and sets the yellow bit, so the yellow light gets on. So it also turns, it then turns the timer for 3 seconds, that is the yellow light timer on, and the red light, and it resets the yellow light and then sets the red after 3 seconds. So then comes the red light, and in this way the loop continues. However, when we press the stop button, it resets all the three lights, red, green and yellow. So this is how the program of the traffic light works. So I show you here in the TIA portal. Download it to the CPU. Search it. Go online. In this HMI, the same as we have discussed earlier, that start stop button, we have configured the events, and for the traffic light we have configured the animations. Here you can see working. This is how the traffic lighting example works here in the scene. This is a very famous example to understand the working of PLCs. So thank you very much for listening. Hello guys. Now I will discuss how to configure analog inputs and outputs in the PLC S7-1200 with TIA port. So here you can see that I have the two main blocks, two main instructions for the analog input and output conversion, Normex and Scalex. For the Normex, what the Normex does, it converts the raw values to the 0 to 1, that is, it normalizes the raw values. And Scalex, it performs a scaling function. It converts the value from 0 to 1 to 0 to 10. Here I have defined it 10. This is the scale, minimum value and maximum value. In this way the analog value is scaled from raw value to the desired value. So here in the network 2 I am doing here a mathematical calculation. I am dividing the input with 2. So here I am getting 0 to 10 volts in the network 1, and in network 2 the 10 volts are divided with the 2. So for 0 to 10 volts we will be getting 0 to 5 volts. Now I have to give this value to the analog output. Here in the analog output I want to display the same value of which I am giving to the analog input. So consequently I have to again apply Normex and Scalex. Here in the Normex I will scale from 0 to 5 instead of 0 to 10. So I am scaling it from 0 to 5. So here I will get 0 to 1, and that 0 to 1 will be scaled into 0 to 2, 7, 6, 4, 8, that is the value given to the hardware. And here I have the hardware address. Here please note that I am using the memory bits here. Memory bit at MW64 and memory bit output MW80. For the actual inputs and outputs I will use here I instead of M. So I will first download it. Since I am using the simulator CPU, so I will first download it. Okay, now I will go online. So this has to be run. Now here I give the value 20,000. So against 20,000 I will get 7.23 volts. So now for the output, so for the network 2 I will be dividing this value with the 2. So here I am getting the value divided with the 2, and now I am converting it back to the raw value. So please note that what I have given input, the output is the same value. So if I am giving the 7.2 volts, I will be also getting 7.2 volts. In the part 2 I will physically simulate it with the CPU and actually download it in the actual CPU and show you the input and output working. So this is how the analog inputs and outputs are configured in the S7-1200. So thank you very much for listening. Bismillahirrahmanirrahim. Hello guys. Now I am showing you the working of the program we have made so far of analog inputs and outputs in the actual PLC. Now the program has been downloaded in the PLC, and in the PLC 1214C we have two analog inputs and there is no analog output. For the analog output we have installed separately a module here. So we see that the analog input that is given is 6.6 volts
and that is given here. And the analog output I am measuring from this meter, that is also 6.69 volts. So how it's working here? Here we see that first here we have the input address IW64, and here we get the normalized value from 0 to 1 through the norm x, and this 0 to 1 value is given to the scale x, in which we scale our raw value, that is 0 to 10. Our scaling is between 0 to 10 volts. So here I am getting 6.616 volts, which I have given to the input module. Now I have here made a calculate block to calculate an output, which is dividing the input with the 2. So for 0 to 10 volt we will be getting 0 to 5 volt. Now I am showing this value here to the analog output module, but now I am scaling it I want to display the same value, same input which I have given to the input module. So I have to keep the values from 0 to 5 in order to get here 0 to 1 accordingly. That 0 to 1 will be further scaled to 0 to 27648 to get the output value. Here we can see that the input is 18293, and here at the output we are also getting 18293. So this is how our analog inputs and outputs are working practically. Thank you for listening.
Hello guys, now we will see how to implement PID controller in S7-1200 and TIA port version 14. So I have made a program already. So I will show you its features. Now here we have the PLC program block. Normally we have the OP1 block, but for the PID we need another block. So I have already created another block, which is cyclic interrupt. How we will create it? We will create it at new block, and here we have the cyclic interrupt here. Now we will click OK and it will be added. So for the PID, first we need to have the analog IOs, analog input and analog output in our example case. Here the analog inputs and outputs are the previous experiment 4. Here we have the norm x and scale x. So here we will be having the input IW64, that's the address of the input, analog input. So the address is normally shown here. If we click on device configuration, here we will be we can see the address 64656667. So 64 to 65 will be the address of first input, and for the other input we have the address 66 and 67. There are two analog inputs in this CPU module, 1214 AC/DC relay, 1214C. So here we will be having the analog input value skipping from 0 to 27648, and from here we will be getting the value in 0 to 1, normalized value. Okay, from 0 to 1 it will then be further scaled. Here we are scaling it from 0 to 10, so we will be getting here 0 to 10 volts. Here we are actually also applying 0 to 10 volts here in the hardware. So okay, now I have created a run here to calculate the output. I am calculating the output by in this run by dividing the analog input with 2, input 1 divided by input 2. So I will be getting 0 to 5 volts in the output for 0 to 10 volts in the input. Now I want to show it to the analog output module, so I will first convert this value to
0 to 1, and then from 0 to 1 I will go to the raw value. So this run shows how to convert a value to the analog output port. So there is no analog output in the 1214C, but we have manually installed an additional block here. Show you this one, and this is basically your analog output, one analog output. We have this in our CPU in the lab, but I am here simulating it in the CPU. So now this is the experiment 4. So now in the PID, now this is the PID. Here is the experiment 5 has started. Now this is the PID component. How it is added? It is added here in the technology. In technology, we will be having PID control, and here is compact PID. We will choose this universal PID with integrated tuning. So that PID block will be here. Now it has many fields. We have to set these fields. For this, we will be having another PID block here in the technology objects. So in technology objects, we will be having two: configuration and commissioning. First, we will go to the configuration. In the configuration, I have inserted the voltage value and automatic. For the input-output parameters, we need to define here what we will use. Here we will use this input and this output. Here we can choose the from two inputs. I have chosen analog. Here I have also chosen the output analog. Okay. However, there are three outputs: output preferred, output, and output PWM. Okay. Now process value limits are from 0, low limit is 0 and high limit is 10 volts, and this is the scaling from 0 to 10, scaling of low value and high value to the 0 to 10 volts. This is in PID. You have to configure it. Now we don't need to disturb these values. These are okay. Now PID parameters. Now these parameters are built-in parameters in the PID. These are basically the time, proportional gain, integral time, derivative action time. Again, please note that this is in the time. This is not the gain. So the equation would be of the PID would be in the time form. Okay. Now we can also enable our manual entry here. We can change these values. Okay. Now this is the configuration, and now on the commissioning part, we will see its dynamic response. So first of all upload this program to the CPU. For this, I need to run the CPU. Okay. Now I start the CPU, simulated CPU, as my computer is not yet connected to the CPU module. So I will download it. It's taking a little time. You have to be patient. Okay, load it. Finish. Now we can go online here. Now here we see that we have here IW, but I don't have here any CPU. So I will change this IW to MW to change it to the memory bit. So I am changing it. It will be changed here from the PLC tags. Go here and change this to memory bit. Okay, and this output. The output can be. There is no need here. Okay, so not here. Now here the CPU must be in the run state. Okay, now let me see it. Yes, now I can give the value like I give 20,000 here, and I have 7 volts here, 7.2 volts. here I have half the voltage 3.6 volts, and then 3.6 I again show it as on the same value. Here you can see here 20,000 we have given the input and 20,000 on the output. Basically we are giving the 10 volts as input, and it is also reading 10 volts on the output. Now please note that the output module we selected here, it can be in the milliamps and in the voltage. In the voltage the range will be 0 to 10 volts, in the milliamps it would be 4 to 20 milliamps. That can be selected from here. I can show you. It can be selected here, and here you can see the analog output, here the voltage. If the current is selected here, it's not showing because it's online. If the current is selected here, the analog output would have to be taken in current form. Now okay, we have configured our PID. Now we are going to commission it. So commissioning, we need to start commissioning, and now this is the commissioning has started, and start PID. So here we can see that we would be having current set point, stable volt, and output here. But here it is not showing because the CPU is not connected. If the CPU is connected, we will see the online trend. Here we will be having the input and set point and the output of the controller. So this is how we configure and commission the PID controller. So in the next video, I will show you in the real time by connecting the CPU with this computer to show the dynamic response of the PID controller. Therefore, I am making this part as part 1, this part of the video as part 1. In the part 2, I will show you the actual response of the PLC by connecting it. So thank you very much for listening.
Hello guys, now I will show you how the PID controller works online. So this is the program I showed you earlier, and you can see here I have given the input voltage of around 6.6 volts to the analog input of the PLC, and accordingly I am getting the output 6.6 volts. So the same value, raw value at the input is showing at the output. Now I will take these two values in the PID controller. PID controller, for the PID controller I will be needing basically an input, which is the PV, process variable. We have a set point and we have a PV, and there will be an error between set point and PV, process variable. That error, basically the PID controller works on this error and tries to minimize the error. So in this way, in this value of the controller is supplied to the control element or control valve, which further changes the process variable. So this is how a PID controller works, basically a PID controller. Now in the configuration, we will configure the PID controller. I have configured it already. I have configured it. It's made for the voltage. In the input, I have selected input per analog and output as output per analog. Process limits I have given 0 to 10 volts because I am giving 0 to 10 volts to the input module, and this is how the scaling has been done here as well as in the PID. We need it, and we don't need to alter these values. Now these are the PID parameter, these are built-in values. If we want to change the values, we need to enable. We can now manually enable change any value if we want to change the parameters of the PID controller. So these are the parameters of the PID controller, or you may say tuning. Okay, now we will go to the commissioning. In the commissioning, we will start here, the start button. Now it will get started. PID controller has been started. Its set point is given as 5, and here we have the input here 6.6 volt. We see that the set point is greater, and set point is lower than the input value, so the controller output will not be generated. So if I sorry, we need to download this. Now we can go online. So now our set point is 7. Started 7. Now the controller output is generating. Yes, now it's showing here. You can see the output of the controller. Now what if I increase the PV value? You can see the decreasing trend of the output. The output now will decrease. The output here will decrease. Yes, now it's decreasing. So this is the dynamic behavior of a PID controller, that we have a set point and a PV and the output action. Now this output action can be altered with the gains, proportional gain, integral gain, and derivative gain. You can make the controller aggressive or less aggressive, P controller, PI controller, PID controller, depending upon your application. So this is a simple demonstration of how a PID controller works. So thank you very much for listening. Thank you very much.